And as in the sessions before, we start a little bit scientific, so that you are able to build your own mind on things, just the most important things to know. And then we will have a deeper look into the energetic gases and gas infrastructure and things which are discussed very heavily at the moment in the energy sector. But like always, we will start to warm up your brains. And if you see this beautiful picture, what comes into your mind regarding to gases? Any ideas? Just say what you imagine.
Powerful.
Light.
Think of zeppelins.
Helium.
Yeah.
Light as in they don't weigh a lot.
Yeah. Okay. This is very, very good answers. Yeah, what we see is the atmosphere, which is contains gases, different types of gases, mainly nitrogen. And we see balloons flying around. They also contain air, but they are lighter than the air around. So we have some effect of gas. And we see the plants which consume gas and which breath gas. So gases play an important role for our life, and they are all around us. But we don't know so much about them, mostly. And I have another question for you, and the question is why a weather balloon will not be inflated completely. Any ideas?
Expansion when it enters higher levels in the atmosphere.
Yeah, but what happens?
It explodes?
Yes, you are right. And this looks like that. So weather balloons are able to really reach the far atmosphere. And this is a picture taken at the moment the weather balloon explodes. But why they explode? They explode because the pressure of the air is less and less as high you came. And so the gas inside of the balloon expand and expand and expand. And if you fill up a weather balloon full at the beginning, it will explode very, very soon. And if you just inflate it a little bit, you really can reach the atmosphere and can take pictures like that very easily. I think this is from a school class, a picture, something like that. So it's no high science. It's something everybody can experience. This is a picture. Imagine or making that what I said visible. So the the atmosphere itself puts pressure to the or the upper layers put pressure to the layers more downwards, and so the pressure in the atmosphere is higher and higher and higher as deeper you are. So if you climb up a high mountain, there's a lower pressure, and so one of the effects is that there's less oxygen in the air because the density of the air is lower. And this is the reason why a weather balloon explodes somewhere on its way to the stars. When we look at gases, there's a very interesting thing. So if we have the same volume of gases and the same pressure, the same temperature, the mass of gases is different, but the number of the gas molecules are similar. This is called the gas constant. And it's very important for us because to have in mind that one molecule of gas under normal conditions, and it's just for idle gases, but it's easier for us to understand it, need the same space in a given volume. So no mind if it's a very light, very small molecule, or it's a very big molecule. The space it's always the same, and so we have gases of different weights, and this is very important because it's connected directly to energetic questions we came later on. Yeah, this is what I already told you. Oh, what's that? This is the gas law. So sorry for going a little bit deeper into the material, but this is important as well. There's a correlation between pressure, volume, and temperature. So we have this gas constant. It's the same for all ideal gases. And if we have the same amount of gas and the same gas constant, it's really a direct interlinkage between pressure, volume, and temperature. And if you keep the pressure constant, or if you change the pressure at the constant volume, the effect is that the temperature changes. So this is what we have normally in all the motors, all gas and gasoline motors. This is the effect we use to drive. But we have it also in the fridge another way. So if you expand the volume at the same pressure, the temperature goes down. So this is very important for a lot of technical things we do with gases. And yeah, you can play around with these variables in all yeah, you can put you can hold the temperature, or you can hold the volume, or the pressure, and the others change in the direction you want to. There are a lot of interesting things in the history of the gas laws, but we don't need it at the moment. Just to, to show you what's behind that. We have a lot of gases which are more or less not combustible, but we have some we can use to carry energy. I think the most common at the moment is hydrogen. And then we have a lot of fossil gases, all these gases which contain C and H, and as well carbon monoxide. This is a little bit different because here the energy carrier is not the hydrogen, it's the lack of one oxygen. So normally we have carbon dioxide, so CO2, and CO is able to react with another oxygen and deliver energy by that. The carbon monoxide is mostly known as wooden gas, and it's especially in the north in Finland. In Sweden, and I think also in Norway, you have some cars driving around with wooden gas motors. So you can also use it for mobility. But we just take a deeper look to hydrogen and methane, because these are the most common gases, and the others are a part of fossil gas, but in the end they are very similar to hydrogen. What else can we see in this table? Hydrogen contains the highest amount of energy per kilogram, so it's we have a lot of energy there, much higher than or more than the double of methane, and the others are very very near together. Yeah, let's go on. Hydrogen, it's some ways special atom. It's the smallest one, and this nucleus didn't contain a neutron, so there's just a proton and an electron. Therefore, it's the lightest of all the elements in the periodic table, and logical, it's the number one of the list, and the symbol is H, as we know. And another special thing on hydrogen, it's the most abundant chemical, so it's disappear very fast. This is also important to know when we talk about storage, and as well the danger of explosions. So it's very hard to have a sufficient concentration of hydrogen in the atmosphere, because it disappears very, very fast, even if you have a room with concrete walls. For such a little hydrogen, the concrete wall is like nothing. It's full of holes, and it disappears very fast. So it's not so easy to create explosive mixtures of hydrogen and oxygen. And it's a part of nearly all organic components. At one side, because it's part of water, but the other side, it plays an important role even in the as carrier of energy within organisms. And hydrogen is as well very important for industrial processes. So fertilizers contain hydrogen, food stuff, so to make oil, or I don't know, the margarine, for example, it's get harder if you mix hydrogen under the fat you use. And in different chemical processes, hydrogen is needed. And as Sylvia mentioned, you can fly a balloon with hydrogen. On the Earth, normally atomic hydrogen doesn't exist, or just exist for very short periods. Normally, it's it's around us in this molecular form as H2. So two hydrogens are connected together. And hydrogen is the atom which or the highest amount of the space, or the how we call it, is hydrogen. So it's we have a lot of big planets and all these gaseous stars which contain high amounts of hydrogen. So we already know that hydrogen is contains the most energy per mass. But there's or it contains much more than methane or even gasoline. And the reaction we use normally is to put 2 hydrogens and 2 oxygens, or 4 hydrogens and 2 oxygens together, and then they react to H2O water, and give a high amount of energy free to the surrounding. But there's as well a problem with hydrogen. So it contains a lot of energy per mass, but it has a very low mass per volume. So at atmospheric pressure, a square meter of hydrogen contains nearly nothing. It's very light, and there's nearly no energy in it. So I have to see. I think the numbers we see down here is liquid hydrogen. So even if we liquefy hydrogen, the amount of energy per liter is low. I think I have to make it to correct it later on. But this leads us directly to the question how to transport hydrogen, and as well as how to store it. So there are different possibilities to store or to transport hydrogen. The most common is to a special hydrogen pipeline. There are ideas to mix hydrogen and natural gas to transport them on the same pipeline. There are ideas of bottle-based transport systems on the road or on the rail, as well as on the sea. And there we have different options. So we can carry it in a gaseous form, as a liquid, or in a chemical form bound to other molecules. And as well, we can convert hydrogen directly to ammonia, which is a fertilizer. So we don't have to do it within Europe if we have not enough hydrogen and we want to import something. There's the possibility to import directly a product of hydrogen. The transport via ships. It's is an option, but not if you use gaseous hydrogen, because the energy density is too low to make it economically feasible to run such a big ship. And normally we have to liquefy hydrogen, which costs a lot of energy, and transport it in deep temperature or cryogenic storages, and even in this form there are a lot of losses during the transport, which can be used to as fuel for the ship itself, but it's very difficult. And then the chemical forms is one option which is discussed very often at the moment. Is liquid organic hydrogen carriers. So you have a liquid where you can store hydrogen in, and then you can transport it very easily. It's absolutely safe, and then at the side you need the hydrogen, you can suck it out of the liquid, deload it, and carry the liquid back to the origin of the hydrogen, and fill it again with hydrogen. So The problem at this technology is that you have to carry around a lot of weight for a little amount of energy in the end. And then there are some special options like molecular-lactic mechanisms and metal hydride storages. So to give you a little, more feeling for the problems in transport of hydrogen, I think at the moment I couldn't find any picture of a hydrogen transport ship. There are just some visions like the one above. There should be one between Australia and Japan, but I couldn't find it as a picture. To liquefy hydrogen, you have to cool it down to minus 252.8 degrees, which is very deep. And you get a feeling how much energy you will need to cool something down to these temperatures. And then there are some problems because a little bit deeper temperature and you have a solid, and this affects a lot of problems in all the system. And even in the state, even as liquid, the energy density is low. We have just 2.7 kilowatt, 2.8 kilowatt hours per liter. This is a third of what we have in gasoline. The other way is to leave hydrogen as gas, but to put it under pressure, so that there are different levels of pressure which are normally used. At 200 bars, we need 55 liters volume for 1 kilogram hydrogen. And this is as well not so much energy. It's 700 bars. It's 25 liters per kilogram. So it's more pressure and or nearly triple the pressure. It's nearly double or in weight per volume, and at normal gasoline you need 1.5 liters per kilogram. So gasoline is as well lighter than water, but you get a feeling which big differences there are between gasoline and hydrogen, even if we use high pressure to transport it. At atmospheric pressure, 1 cubic meter of hydrogen contains 3.5 kilowatt hours of energy. So this is nearly a third of the energy density of methane, and even less of that of fossil gas. So fossil gas, normally it's not pure methane, it's a mixture of methane and butane and propane. But what we can see here is if we have a cubic meter volume of pipeline, for example, and the same pressure, we could just transport a third of the energy content if we switch from methane to hydrogen. So this is something important to know. The transport problem is very big with hydrogen, and I think this is the key question of hydrogen infrastructure and the future of hydrogen. Here,
Can I ask you a question, please?
Yeah, of course.
I know that with normal fossil gas transport, a big problem is gas leaks, and obviously then methane escapes and has a really high warming quality. Yeah. What would happen, and has it really been studied, if large quantities of hydrogen started to escape into the atmosphere, for example, in a gas leak from a pipe?
Nothing, nearly nothing. A part of it will react with oxygen to water, but it's very unlikely that you get a explosive mixture. So something else, if there's a leakage of a hydrogen and oxygen pipeline close together, then it could be problematic. But hydrogen itself, it's not toxic. It's part of the atmosphere. It's mostly in the, because of the pressure in the upper side of the atmosphere, and it will disappear very fast. And you, after some minutes, you wouldn't measure anything on that place.
Okay. And where does, so I guess if it released again, it would just go back into the atmosphere without causing any problems. But where does it come from in the first place? Is it sucked out of the atmosphere, or is it taken? I think.
The production of hydrogen.
Yeah, where do you get it from?
Normally, you crack water. You have this. You can reverse the this process. We shown you where here over the butt. So if you have water, if you have 2 molecules of water, you can crack it into 2 oxygen and 4 hydrogens. This is electrolysis. There are different technologies to do it. Membrane electrolysis, where you have something like a wall in between, and there are technologies where the hydrogen itself could pass to the wall and the rest not, or others where the oxygen can pass to the wall and the hydrogen not. And as well, we have acid electrolyzers, but the way is normally the same. You need pure water; it have to be pure, but then you could crack it very easily, and you can do it at home as well. If you put a wire into a glass of water, you will see bubbles come up, and this is hydrogen and oxygen. Yeah, be careful if you try it.
So I guess there's a thing about water use then to create hydrogen. Does it, and obviously you'd have to purify it, but can you use seawater? Because if it's going to start using up loads of fresh water, then it's going to cause massive problems, right?
Yeah, we can use, of course, we have to purify seawater, but this is well-known technology, and we can do it very easily as well with remote osmosis, so with renewable energies, and yeah, as well you need some membrane in between, and you can purify the water to very reasonable costs. I think it's $2 or $5 per cubic meter of water.
Okay.
So this is not a problem. You should do it, or big plants should do it, and don't grab the drinking water in regions where this is a problem for the citizens. But the technology it's very well known. It's easy to do.
Thank you.
Here again, this might look a little bit complicated, but the information we get out of it is if you put 20% hydrogen into a methane pipeline, the energy content of a volume of this gas goes down. This is one of the reasons why even a blending of 20% hydrogen into natural gas would just lead to a reaction of CO2 emissions, or of not the emissions of methane leakage, or but just the CO2 during the combustion of 7 to maximum 8%. So it makes no bigger sense to blend natural gas. This is the information we get out of here. And yeah, you just should have it in your mind. There are a lot of dreams of the gas industry to use it as an in-between, but in the end it makes no sense, especially if the hydrogen is not produced with green energy. The content goes down to 3 to 5%. Then there's a question: do we need transportation of hydrogen, or could we use storages on site? So the old decentralized decentralization discussion. What we can see here is out of an Agora study. They put an hexagon over Europe and looking into each region and try to calculate the differences between costs of local storage and transport, pipeline transport. And as you can see, if you have a low consume of hydrogen in this area, it could be sensible to use local storages, but if you have higher amounts, it's much more cost efficient to use a pipeline grid. To store or a big part of these costs are the costs for storage. So hydrogen storage is it's not cheap, because you need a big volume to store a little amount of energy. And the most cost-efficient way is to use salt caverns. So what they do, we have big salt layers, which are some 100 meters high in the underground, and you could just drill a hole into them, and then you use water to make a hole in this salt layer, and then you can store different things in there. You get very big storages. At the moment, they are mostly used for gasoline and oil and things like that. But you can easily use them to store hydrogen in a safe way and with more or less low pressure. So this is by far the cheapest way to store hydrogen. And having that in mind, you can map Europe for the geological conditions where you could store hydrogen in salt layers, and these are the little bit orange parts. So we have in the north of Germany and Netherlands, and as well Poland, a little bit a big salt layer. We have here in the Northern Sea a big salt layer, a little bit in Great Britain, a bigger one in Spain, and in some other places. So these are the locations where we should store higher amounts of hydrogen in the future. Because this is one of the ways to store additional renewable energy in the future. But this is bound to locations. How should we use hydrogen? So we see it's not easy to transport. It's more or less easy to produce, but it's it has this worth because a lot of energy is needed for, if you put everything together, the efficiency of the production, the efficiency of transport, and then the efficiency of the end use. So we should use it carefully, because it will be more expensive than direct use of electricity, and by far. Here we have a nice graph. I hope you can see it more or less well. This is from a study from the Florence School of Regulation, which Antina has circulated some days or a week ago. And at input, we use the different types of hydrogen production and different sizes. But at the moment, you can use efficiency of 75% for electrolysis as this is a good number to calculate other things. So we enter the system shown here with 25% energy losses, and then we can decide what to do with hydrogen. If we burn it in a steam boiler, which itself has a high efficiency, we came out with 70% of efficiency. If we use instead of hydrogen electric steam boiler, we have 95% efficiency. So to make hot water, hydrogen is not an efficient solution. If we use it for the heat production for our homes, we enter again with 75% of efficiency, and then we have a condensing boiler, which also sucks out the energy of the water vapor and the burning gases. You have to multiply these numbers, and then we get come out with 75% of efficiency. If you use instead of that a heat pump, which is a normal air heat pump here, which has 300%, because we use as one part electricity, 3 parts of surrounding energy, so we get this high efficiency. And it's much higher if we use earth heat pumps. And a heat battery, I don't know exactly what they mean with that, but in the end, heat storage could be meant. We came out with 250% efficiency, so much higher than the direct use of hydrogen. If we use hydrogen to produce electricity again, we and use a fuel cell with it, this is very high for a fuel cell, 50% efficiency. We came out with 40%. So we need 100 kilowatt of energy in the entry, and in the end we get 40 out. So we lose a lot of energy in between. If we use instead a battery to store energy, and we have calculated with more or less big losses. So this is a battery which runs over a longer time, or which stores the electricity over a longer time. We came out with 85%. So yeah, much more efficient than the use of hydrogen. If you use hydrogen to drive around, of course, the bicycle is more efficient. But if we want to drive a motor-driven vehicle, and we use hydrogen and the battery electric motor and the fuel cell, so we even use here the energy for bremsen
Great.
Yeah, from braking. We used the energy. We came out with 30% of efficiency. If we use a direct electricity car, we have much higher efficiency with 75%. And then there's a special question. A lot of this hydrogen waste need a lot of raw materials, and so there's another reason to be very careful with the use of hydrogen. but we have here's another map or another picture I like very much. Here's zero line, and here we compare interest, or we compare hydrogen applications with the best other options. And you can see what we have seen in the picture before. Here in another picture, a decentralized hydrogen boiler is no option. We have a big need of hot water, so this is the spot is very big, but we are in average 80% less efficient than to use other forms of water heating. With hydrogen cars, we are in the same area. We don't need so much energy at all, but we are 70% less efficient than the best other option. There are special usages like heating plants, so in district heating situations could make sense to use hydrogen, but as well transport with trucks, hydrogen trucks, makes no sense. There are other options to for the heavy transport which are much more efficient. Ships and trains could make sense if we have no not electrified lines for trains and ships, at all. And then we have some need in industrial heating plants, so where we need to generate high temperature, high temperatures for high process temperatures. And then we have the field of fertilizers, and hydrogen is primer molecule source, so not energetic as on the atomic base. Here again, to have a deeper look into the no regret industrial demand of hydrogen table from the Agora study. Here you can see we have refineries, ammonia production. This is fertilizer, methanol for this is a liquid form of methane. You could use this for different things. I don't know what they have in mind with that at the moment. And then to recycle plastic, to make new plastic, you need hydrogen, and for the steel production. And you see here a phase out for refineries, and a higher and higher amount of hydrogen needed for steel production and for fertilizers, and as well for plastic to replace fossil fuels here. So this is a very interesting study if you want to deepen your knowledge and have a look into this Agora study. They mapped the industry with with a no regret hydrogen demand over Europe to figure out if we build pipelines where which regions we should reach and what makes sense. And you see here the dark blue spots. There's a very high need for hydrogen. And then we have some islands with very, very low. Zero means not zero, it means below, I think, 1,000 terawatt hours. But in the end, they came out with 4 regions in Europe where a high hydrogen infrastructure would make sense. So this is here northern French, Belgium, Netherlands, and part of Germany. We have here Poland, and I think this is Latvia. And here, I don't know, Croatia, Serbia, something like that. No, this is Greece already. So yeah, in the southeast of Europe, and in the north west of Spain. What you can see is they also calculated which form of renewable energy would be available for the hydrogen production in this area. And you see the blue is wind in the north. We have some spots where hybrid wind and solar energy, primary energy is feasible. And then we have in the south, mainly solar is primary energy. Then a lot of people have dreams from big hydrogen, green hydrogen imports from outside Europe. What we learned is that's very problematic to transport hydrogen via ships. So a very big ship carries a very low amount of energy, and in the end, if it has to drive around the world, maybe it loses more energy than it carries. So a pipeline is the way the best way or the most by far most efficient way to transport hydrogen. And if you look into the regions of North Africa, you can see in this map the production costs for hydrogen. So they take really a lot of things into account, infrastructure and securities and a lot of layers. And then in the end, we just find some very little spots where it's cost efficient to produce hydrogen. In Morocco, this is Tunisia. It's more expensive. We have a existing gas grid to this region, but the amounts of hydrogen we could import from these countries is very, very, very übersichtlich. It's not so much, and if you calculate it, they want to use part of it their own. This could only a part of the hydrogen we need in Europe. So we have to produce our own, and we need much more renewable energy than for the pure electric way. Here some cost estimations out of this Fraunhofer study. So the costs between pipeline from Morocco and Tunisia and by ship. And you could see here the liquefaction consumes a lot of money per contained energy, and the most reasonable ways are pipeline transport from Morocco. Okay, to come to the colors of hydrogen. The gas lobby mentioned in I don't know, in one of the last conferences where Eva took part. All colors matter. So but they mean not all colors of people, they mean all colors of hydrogen. And we have a lot of different colors. We have so-called gray hydrogen, which is produced via steam reforming from natural gas. So you remember we have this CH4, so 4 hydrogens and 1 carbon in between, and you can suck this hydrogen out by steam reforming, but the effect for the atmosphere and for the climate change is very low. We have Turkish or turquoise, how you spell it? You know what I mean? Hydrogen.
Turquoise.
This is, huh?
Turquoise.
Turquoise.
I think so.
Yeah.
Yeah. Okay. This is made by pyrolysis. Pyrolysis is a form where you generate in the end solid carbon, so graphite and hydrogen. It needs a lot of temperature and energy as well, but this is a little bit more climate friendly than the gray hydrogen. You could generate hydrogen from out of petroleum or from coal. Oh no, this is negative. No, this couldn't. Sustainable high, greenhouse gas pollution, low, medium, high. Okay, yeah. This is even lower than to use gas. We have this pink hydrogen, which especially French.
Can I ask, Holger?
Yeah.
You say even lower than from gas, but according to the chart, gray hydrogen is the worst.
It's the worst, yeah. And
Yeah, that's correct.
Yeah, to use coal or petroleum, it's better than to use gas.
Okay.
I think this is based on the methane emissions, and here you could not reach a high purity. So there's still some methane left in this hydrogen. Blue hydrogen, this is, yeah, and here there's no CCS with it. So, okay, you can do more or less the same with CCS, then you are much better, as well better than coal. And we have this pink hydrogen, the dream of the French atomic industry to use nuclear power during the times we have high amounts of renewable energy to produce hydrogen. So they don't have to shut down their atomic plants. Then we have hydrogen from biologic processes, from fermentation, or from biomethane. So biogas normally contains methane and a lot of CO2 as well, and you can suck the CO2 out. And if you use or if you reform the methane out of a biogas plant, this is the carbon is carbon which was captured before from out of the atmosphere by the plants. So you have no additional carbon in the cycle.
Oh, can I just stop you there a second? Sorry.
Yeah.
According to what we planned for this session, we've only got 2 minutes left.
Okay. I'm nearly okay. Green hydrogen. Let's see. There, I'm nearly done. The message is a blue hydrogen is not CO2 free. It's just a little bit purer on CO2 equivalence. So be careful with all the things which are sold in different colors. The only thing which is discussable on my understanding or from my mind is green hydrogen. And here we are at the end.
Holger, I have a quick question.
Yeah.
Like, in the way the terminology that the Commission uses is the green hydrogen, no, it's renewable hydrogen, and then it's low carbon hydrogen. Where with renewables, I understand that they do not mean just wind and solar, but they also consider the one from biomasses. So that the other two green boxes, I think that they consider all. But when they refer to low carbon hydrogen, do you know? I mean, I would exclude the gray and the coal. I mean, what is included in the low carbon hydrogen?
As I know at the moment, blue hydrogen, pink hydrogen, and it could be the Turkish one. I'm sure gray hydrogen is out for sure, and I think this is as well not in the discussion, but all the rest.
Okay. Well, no, thank you. Yeah, it's, I mean, I know that it's, I was thinking about matching colors with Commission terminology.
Yeah, they use another terminology, and it's the gas lobby tries to find new descriptions for the old things to bring zu verwirren, to make everyone crazy think about.
And I think that's an important point to make to the rest of the team who have not been exposed so much to these discussions. As RGI, we say what we consider as trustable is hydrogen from renewables, because this usage of the terminology with the colors, which is apparently also not 100% clearly defined and clear cut, is a bit of a smoke bomb. You use a type of wording, but it's not fully precise on what you're really talking about, which doesn't help to come to clear conclusions what you want to push forward and not, and therefore as RGI we abstain from using the color terminology completely.
And we add variables, renewables. I mean the terminology of variables, so that it's wind and solar, and we do not open other discussions on hydrogen produced from biological procedures or biomethane. So I agree.
Other questions?
I have a question, but I know that the session is over, so I don't know if I should
mind.
wait, Liam.
Everybody who has to leave could leave.
Much longer, but another 5 minutes would be fine.
Okay.
I have a question, because in the offshore area is discussion at the moment that you can do hydrogen directly at the offshore. You can also use the turbines in the windmills for doing so. And I was just wondering if you could, I know it's a big question, but if you just could say shortly what is meant by that. So can you put the hydrogen plant within the wind offshore, or do you have it next to it out in the offshore area? Will it take up more space, or will it have impact on them?
Yeah, normally you would build up something like a converter station, so a platform near to the wind park or within the wind park, because you need something where stuff could stay and sleep, and the windmills are normally very difficult to reach, especially during bad weathers. And it makes sense to have it more central, so to use the energy of all the different turbines in your park one central point.
Thank you.
You're welcome. Other questions? No?
Sorry, I have to leave. Thank you.
Yeah, then